So let's get started. Just for a reminder for people in the Zoom, we have one class less because of the typhoon. Hopefully, we don't have one more typhoon, and hopefully, we will have all the class we need to have. And if we need to make up, we will let you know. I try not to do make up because I mean, it's not I don't like to have the class. I actually enjoy teaching, but the problem is it's very difficult to make the schedule that works for everyone. In the worst case, if we need to make up, then we try to save it for the last few classes. And if we need to make up, we try to make sure that if you don't have time, you can still do the Zoom, or the Zoom recording will be available in that particular case. So in that case, let me start the sampling distribution. Just one more reminder to let you know is the homework is available already. So homework 3, I think homework 3 is available. Assignment 3 is available. Will be this Sunday. You have to submit it just to make sure. And the solution for assignment 2 has been uploaded, so you can check it out. If you have any question about the grading, just email the TA for that, because I'm not the one who grade it. If you have problem with the solution, you should also ask TA first. If you can't resolve, TA can talk to me, but TA will be the one who doing the grading or other thing. Okay, assignment 3, and just reminder, the final test is on the last Friday. If you are not available, let me know, and then let's finish this. Or for those who coming late, and because we missed one class from the typhoon, so maybe the one immediate consequence is next Monday probably we will have also a lab section, not here but in the lab again, because maybe this Wednesday we have a lab section, but we may not be able to cover everything in the lab. Okay, so once I book the room, I know which room we're doing, but likely the same room that we have been doing. So today's goal is going to finish this relative short topic. It's about sampling distribution. Okay, so just to give an idea what we are covering for this class. Okay, and this class will be basis for the rest of the whole course. Okay, because the rest of the whole course is starting the inferential statistics. Okay, trying to use data. Okay, to tell us to draw some inference, to make some regression analysis, to try to talk about the causal inference, to say from the data we start to make decision. Okay, and the problem is we never able to obtain all the information we want to know. Okay, suppose you want to know the income of everyone in Hong Kong. Okay, potentially if you have data from the in-net reference department, you know everyone's income, you can average, that's fine, right? And that is government can know. But other than that, I mean, if you are a independent researcher, not able to obtain that, right? What you're going to do is that obtain, talk to some people and try to see if the data is representative of the whole population you want to do, right? Or for income, probably you can easily know, right? But if you try to ask how many people in Hong Kong like say Mira or Era, I don't know. I mean, I don't know what was the thing, but there's some handsome guys and looks like, I mean, many people take pictures. I never understand why. I mean, my friend also never understand why, but maybe there's a teenager thing or young people thing, but whatever. I mean, how many people like the 5 or 6 handsome guy over there, and some people like it, some people hate it, right? But if you ask everyone in Hong Kong whether they like I don't know what's the name. I mean the guy who have a golden brown hair, say Zhang Tao, is it Gang Tao? Is it? I don't know what is the guy name, but anyway, whatever. And then you have to ask everyone, right? The problem is like you are unable to ask everyone, and you have to ask a subset of people whether they like it or not, right? And then you want this subset of people to be representative of the everything, right? The whole Hong Kong, right? You don't care about whole Hong Kong, right? So you don't care about the subset of people, but you want to just ask some of the people to try to make decision of to guess what is happening in the whole Hong Kong. So then depend on what kind of sample you get, you have different decision to make, right? Because you may be likely that you draw a sample that is biased, right? If every time you draw a non-so biased sample, then it's okay, right? But otherwise, you may not get a good outcome. So what we are doing here is trying to study, okay, suppose you get a sample, and in particular case, the sample mean or the sample proportion, right? In the case whether people like particular stuff, it's true or false, right? It's yes or no question. Then we want to know this kind of answer, and that is what the sampling distribution comes in. We will try to see the sample mean, like the income, or whether people like particular stuff, right? And then we want to know it because it really depends on what kind of sample you got, right? So we need to see. The thing is, if you have more sample, right, then what you do is more accurate, right? Suppose you collect everyone, then you must get the right thing, right? But the problem is that it depends on the sample size, right? How large the sample is, then you would decide how accurate they are. So that is the goal of this. Any question before we start? So that is the goal, and that will be the basis for the rest of the course. So next, after this, we talk about estimation, right? It's based on what the data we have to guess, right? So what first is the example as I look at the income of the housing size, right? Because income, maybe government know, right? How big is the house is not easy to see, right? Government doesn't know it. And the question is, I want to know what's the average living space, right, per square feet for each person in Hong Kong, okay? And that would have to get a subset of the data, right? And the thing is, I will know estimate, right? We want to know how much is it, how big is the living space. We have to make an estimate, and based on the data. Okay, that's what we'll do in the next topic, basically next class. And after that, we will do what we call the hypothesis testing. That is, we have some claim, we want to see the data that support the claim or not. So an example would be, we'll be looking at, say, some people claim, say the living space in Hong Kong is similar to Tokyo, or it's very small, those kind of thing, and comparison, and this kind of thing where the data support what you claim is the after the estimation, we call it hypothesis testing. And afterward, we do ANOVA regression. And basically what these two topics is trying to discover how two variable related or the causal impact or correlation, right? To see whether something affecting other thing, right? Maybe some people claim, as I said at the beginning, whether people like the Mura era is those younger generation, so on and so forth, right? So whether the age would be determined whether people like it or not. Okay, so that is the idea behind. Okay, so let's get started. So so we focus on sample. We talk about sampling, and how to do sample is a very deep subject that we don't have time to cover. It's a very technical subject because you really want to say, want to study certain thing, I want to collect some data for it, right? How to collect appropriate data is a very difficult thing, right? Because you want the data to be representative of the whole sample, okay? So it will be, if we know more about the population, what we want some subject study, then we have to change our sampling method, okay? So we consider the most simplest one, okay? But I'll talk about some more advanced a little bit, let's touch a little bit surface. So it's like the following. The ideal consideration would be you have a technology that makes sure that every single element is being selected randomly, okay? Imagine a case you are talking about whether people, say, I want to ask what is the living space right? For average living space for everyone. So what you're going to do, maybe you try to do a survey in a say Mongkok or in Central, right? Or somewhere area, right? But in that case, you're missing those people who live in rural area. In the village, you never go there, right? So you're missing those people. Or you try to ask how many people like Mura, right? The problem is you are through a web survey, right? The problem is you are both basically looking at those people looking at the web, right? Say my mom, my parents probably would not look at the web as much as we do. Then probably they will miss the survey, and you will not catch those data. Okay. So the question then now is like this is actually every element has equally probably being selected. It's a very demanding. Okay. So I have each element has to independently. This is also very demanding. In the sense that if you say I try to ask say how to collect data, how many CK student like Mira, okay, for example, and in that case, if I do the survey in say the simple convenient ways to do it in the subway station, right? You just like there, right, and just try to ask people whether they like or not. Then in that sampling, the problem is for those people who are living in the campus, they rarely go to the subway station, right? Basically, that's just they suppose when I was a student, I was in the NA is here. I living in here, then I never go down to the train station, which is right. You don't have to, unless you really have to. But in that case, you don't actually fill in those survey. Okay, so that's why. And the problem is why it's not independent select is because when you select the first guy, okay, the second guy is also the guy who actually go to the subway station. Okay, so the first one, if you pick someone in the train station, you're unable to pick me, unlikely to pick me because I'm not going to the train station. Okay, so each observation is not independent. Okay, if you want to be independent, say in CHK, what you do is you take one guy, say in NA, okay, and then what you're going to do is you hop on the school bus, okay. Suppose the school bus goes everywhere, right? Randomly drop down, you ask another guy, okay. If you stay in NA, keep asking people, then basically you are talking. Each observation is correlated, right? It's related in some sense. And so the first two is the thing we rely on, okay. And that if you have this two nice property, okay, that means that each observation, because randomly select, independent, will follow the same distribution as population. Okay, what does that mean? It means that mean member population has a distribution, right? Say suppose you're asking the living space, right? I don't know. This is the living space. Then maybe you cannot go to negative, right? So I mean, I hope it's not going to be something very small, so something like that. I don't know what's the shape, but this is the distribution. Okay. Although we say distribution, doesn't mean that that has anything about probability. Okay, because it's underlying the people this is a bar chart or histogram, right? There's no distribution there, so there's no probability there. But just saying that some people live in a bigger space, some people live in a small space. Okay, but the fact that if you try to draw one guy from here, okay, under simple random sample, this becomes the distribution, right? Because it become a probability. So let me repeat the statement because it's very important to distinguish the two. The population, subsequent study, say the living space of your family in say for CHK student, there may be definitely there's some people living in a bigger space, some people live in a small space. There's no probability there. Suppose in the world we have the data, right? That everyone lives somewhere, right? The space, there's no probability. Some people live in bigger, some people live in smaller. But we're trying to do simple random sample, try to ask someone, okay, randomly draw some guy, okay, and that may be some guy here, some guy there, some guy here, okay. If this is satisfy what we want, each observation is basically draw there, right? And draw there, then they will follow this probability. Is that clear? So you're more like suppose more here people here likely to draw here. Is it make myself clear? So suppose you are asking, okay, another question, a proportion, okay, proportion. So Maybe you're asking people who like the mirror, they don't like, right? Then maybe you, I don't know how many students in CHK, maybe so consider you have maybe just B school, right? B school maybe 1,000, just make up a number, right? 1,000 students, right? Then maybe you ask, I don't know how many people like, maybe just make 600 like mirror, 400 don't, okay? I mean, that's a random number. And this is a distribution, right? Suppose we have, no, this is the number. And now you randomly pick a guy, or good, I mean, some student, okay? Then the probability that the student like the mirror will be 0.6, right? Because will be, right? You randomly pick up one guy who don't like, then will be 0.4, right? So that is the idea, is like this is a number underlying there's no probability. But if you have the distribution, right? But you randomly pick up a guy, this become probability. Okay, and no matter which, if suppose the draw is independent, okay, happen to be you can draw the same guy, right? Because each draw has no dependence. Okay, so then every draw you have is this probability. Okay, it's for the same. So that's what this means. Okay, of course the same distribution means that every draw has the same mean and same variance and zero covariance. Okay, the first draw is they like mirror, doesn't mean the second draw they like or not, doesn't tell you anything because it's draw independent. Okay, you happen to be the same guy can be drawn consecutively. Okay, there's no sampling with replacement. You draw a guy just like you have a list of students. Okay, you just go through the list. Okay, random number generate. Maybe you just have a names over there, just throw a deck and get a guy and do it again, right? Can land on the same name again. But what it means is you have simple random sample, you have same mean, same variance, and zero covariance. Is that okay? So this assumption, okay? And so that is what exactly this means, okay? If your simple random sample, each observation have the same as the population one, variance same as the population one, and covariance 0, okay? So the question is when you actually do your own sample, okay? Suppose you want to do it for your project. I'll talk about it more about project after we talk about estimation, because other than you can know what to do for your project. But high likely, don't worry, it's like a few pages of work. It's like a little bit more open-ended assignment. So don't worry about the project right now. And the question is, suppose you do a survey, right? The question is like how you actually do it when you know that the world, the data is not uniform. What I mean is, look at the US. I don't know whether you're aware of any US survey, expected political survey, right? Look at the election survey. Okay, what they do is they randomly pick up some people, ask them whether they support this candidate or not, or support this policy or not. But the problem is, you do a random sample as an issue there, because you know that people are more likely to, when you ask political question, people are likely reflecting their party affiliation, whether they're Republican or rather they are Democrat or independent. Actually, a lot of difference. Okay, you may happen to be in a random sample based on telephone or web survey. You may have more Democrat than Republican, or you may have more independent. Okay, and we know that Republicans tend not to reveal their views, right? So in that case, if you have the data you got has more, say, one of the things, suppose you are unlikely that you make a survey, you have a lot of Democrat. Okay, what we're going to do, you have to downgrade those. Okay, so that's why you have to readjust the sample to make it more better. And or in the case that you are going to collect data from CHK, say, okay, and we know that you want to ask, we want to see, say, which canteen has the best food. Okay, say each school have each college have their own canteen, right? And then probably people in then you will know that each college have different student base, right? And if you do really simple random sample, say suppose you just randomly ask people in the train station or in the central library, the problem is you will oversample from the 4 original college who has some more student than the other 4 college, right? So you have oversample from that, okay? So you have to adjust, okay? And the other way around is to do it is not to adjust at the beginning, you just not to adjust at the end, you adjust the beginning, okay? So we know that, I mean, you have more students, okay, in all the 4 college than the new one, okay? So then you would just try to go to, say, in NA, you collect 20 students, right? In all the 4 college, you collect, say, 20 students, and in smaller college, you collect 10 students, okay? Supposing the old college are twice as much as the young one, right? So proportionate, each college, you collect proportionate number of students, right? Then you would have a more fairer sample. So, but that would be a technique that would be used when you actually work out stuff. But just let you know how you're able to do a survey, right? Suppose you are a marketing manager, right? You want to collect whether how is your feedback for your product, right? Then you probably need to do surveys, easy to do, right? Because internet where people easy to do. But most likely some of the people, depending on your customer base, right? People actually may be much older age. They may not telling you from the web, right? So you have to do for the other channel and adjust for those fact that they are less likely to respond from non-web means, okay? But that will be beyond our scope. We just assume that with the data that satisfy this, okay? And when your data not satisfy this, you have to make some way to adjust. Either adjust when you collect data, as I said, right? You just do what they call stratified sampling. You just go to each group and do some random sample, or we adjust it later, okay? The data, it depends on the characteristic, you adjust it accordingly, okay? And actually, there's a similar thing we talk about the vaccine thing, right? You talk about vaccine or the infection, turn out to be depending on what group of people you have, right? You adjust accordingly, right? But anyway, I think I should talk about sample mean, okay? Sample mean is the thing we care most. Actually, there are a lot of things we can do with sample, but as I said, we care most is sample mean, and later we'll talk about sample proportion. But sample mean is it's a continuous random variable, right? And the mean is like this, okay? It's just sum of them over n. Do note that here xi, I have the capital letter because each one is a random variable, okay? Depends on what number you draw, okay? Each one is random variable. It's not observation, not number, okay? These are all sample is a random variable, depend on what you draw. That means that the sum of random variable, okay, or average of random variable is also a random variable, okay? The sample mean is also a random variable, okay? That means that if you have consider we have the population is here, right? And these are all the data. Suppose you are going to draw one sample here, you can carry sample mean, right? And suppose you have draw here and a sample mean, okay? So it depends on what kind of thing you have drawn from it, you have different sample mean. So sample mean is a random variable because if you draw only one thing, okay, you just click, you hit this guy, then you get this guy, right? Depends on where the pen ends on. So this will get you different sample, give you different sample mean, okay? So that would be a important thing. This is each observer is a random variable, and this average of each observation will also be a random variable, okay? The next thing is something is not very surprising, is coming from the linear property we learn about expectation, okay? Remember, it's expectation of the sum with sum of the expectation. If you remember this, expected x1 plus x2. Okay. So that means expectation, you can separate two of them, right? That's what we learned in the previous class. Okay. And here, what we have is sample means divided by 2, right? Because this is the sample mean if you are only 2, right? And each one have the same observation mu and same mean. So mu plus mu over 2 is mu. Okay, so that is the proof behind. I'm not going to go over the proof, but you just change to n, the same thing. Okay. But what it means is the mean of sample mean or experimental mean is also a mean. So just to see the significance, just to look at it here again. So suppose I don't have any, I have somewhat, this is the distribution of underlying distribution, right? But this is also same as the each observation xi, right? And suppose I draw one sample, right? Suppose I happen to be here, here, and here. Okay, this is I draw 3 observations from here. Okay, and then the sample mean may be averaging out somewhere here. Okay, maybe this is x bar. Okay, and next time I do another sample, maybe here, here, maybe a little bit further, right? Let's say I got another sample mean here. Okay, and for each sample I have sample mean. Okay, so it means that the mean of all these sample mean, okay, will be same as original, the mean, right? This x underlying have somewhere mean here. Okay, what it said is if I do many sample mean, I do many sample, each sample of the sample mean, and average of those sample mean will be same as the mean of the original underlying thing. Okay, so just go back to, oh, I erased the mirror thing, right? It's a good thing. Suppose I want to know, it says 600 people, right? Remember the mirror question, 600 and 400, right? Okay, so maybe I have in one sample turn out to be the proportion is 0.8, the other maybe 0.7, maybe 0.5, maybe 0.9. Then you have many of them. The average of this go back to 0.6. Okay, the proof is here. Okay, but I'll give you an example to convince you this is also true. Okay, so this property is very interesting. Later we'll talk about next class. It's called unbiasedness, which means that if I want to use the sample mean, okay, to guess the mu, this is what we want to do, right? Just like I want to know how actually other people like mirror, right? In that case, I use a sample to estimate the true underlying thing. We don't know, right? 600 actually in the world we don't know, but we only get this estimate. Actually, you only get one. You don't get many, but only get one. But what we're saying is, suppose we do a lot, and average of those actually meet our target. Okay, there's no miss, exactly match. That is called unbiased, which means that there's no bias. Okay, this property actually related to what we learned in the first topic. We talked about sample variance and population variance. And why we want sample variance? Why n-1 is because this unbiasedness. Okay, that's why I said, right, when you do sample variance, you estimate the true variance, you would be doing a better job. Okay, and we'll talk about this next class. Okay, but first thing is why we have been using sample mean as a good thing, because sample mean is a good thing to about population mean. Okay, but this is the first outcome. Okay, the next thing we want to talk about is an example trying to convince you that the sample mean Okay, indeed, the mean of sample mean is population mean. Okay, this is an example to convince you what we said is right. Okay, the first part is suppose the population is only 3 number 1, 2, 3. Okay, and you can calculate the mean, which is adding up all the numbers divided by observation, right? There's no probability here, right? Only in the population, you only 3 numbers 1, 2, 3. Average of these 3, of course, is 2. Okay, the first question is we consider sample size of 1. Okay, sample 1. Okay, we just collect one sample from this population 1, 2, 3. So what will we be getting? Okay, 3 numbers. Okay, you just draw one guy there. Okay, it will be 1/3 of the time you get 1. 1/3 of the time you get 2. 1/3 of 3. Is that okay? Because what it means is 1, 2, 3 there, you have considered the 3 balls. Okay, now just close your eye, pick up one ball. Okay, and put it back, pick up your ball again, close your eye. Okay, calculate how many times you get 1, how many times you get 2, how many times you get 3. Right? So it's 1/3 of the time you get 1, 1/3 of the time 2, 1/3 of the time 3. Suppose you close your eye. Okay, in that case, let's go back here. Is 1/3 of the time you get 1, 1/3 of the time you get 2, 1/3 of the time you get 3. Okay, so if you get 1, sample mean is 1, right? Only one observation, the means of itself, right? The 2 sample mean is 2, the 3 sample mean is 3. Okay, so the expectation of the sample mean is 2, because 1 times 1/3 plus 2 times 1/3 plus 3 times 1/3. Okay, so mean of the sample mean is also 2. Okay, so let's do less trivial one. Okay, let's do 2 sample size of 2. Okay, if you do sample size of 3, that's also the same, it's 2, because only sample size of 3 is just everything. So it's also a 2, right? Because only have probability 1 that you have 1, 2, 3. Okay, so let's do the other cases of sample size of 2. Sample size of 2, you either have the following. So 1, 2, 3, 1, 2, 3. Okay, and do note that each draw is independent. Okay, so it's possible that you have 1 and 1 again, because you close your eye, draw 1. Okay, okay, it's 1, put it back, close your eye again and draw it again. Okay, then you have 1, you can have 1 at both times. Okay, and because each draw is independent, right? So it's simple random sample, so the probability that you get 1 entry 1, 1 is 1/9, right? Because it's the joint probability and the independent is multiplied, right? 1/3 you draw 1, another 1/3 you draw 1. 1/3 times 1/3 is 1/9. Okay, and you have 1, 2 is also 1/9 for probability. Okay, but the average of 1 and 2 is 1.5. Okay, this number are the average, sample average. Okay, you have 2, 1 is 1.5, 2, 2 is 2, is your 3, 3 is 3. Okay, your 2 and 3 is 2.5. Okay, so entry or sample mean. Okay, and probability of each entry is 1/9. Okay, that means the sample mean is 1 times 1/9 and 2 times so 1.5 times 1/9, and you have 2 times or 2. Okay, and you have 3 of 2, right? That's at the end you get this 2 again. Okay, this example convinces you that, which you have already seen here, the mean of sample mean is same as population mean. Okay, so later you will see why we need that. We'll be needing that in the next topic, the next class. But that is the very important property. The mean of the sample mean or is same as population mean. Okay, that is what this statement said. Okay, but do note that, I mean, although this is a very nice thing, we only have do 1 sample. Okay, in the real world, we never do 9 of them. We only do one of those. Okay, happen to be in your case, when you do your sample, you may end up here, end up here, end up here, end up here. Okay, but most likely you are again in the middle. Okay, so that's not that bad, but that is what we're saying, right? If you have keep doing this or doing a lot of sample, then actually you're going to be closer to the center. Okay. So the next thing, okay, here I talk about the mean of all these sample mean go to here, okay, and the next thing we want to show is the following. And if we keep so we want to first sorry, I want to ask is what is the variance of this, okay, and it turned out to be the formula is like, it's actually not that difficult. Actually, you can prove it. It's the same thing. You just change this expectation. Okay, I'm not going to prove. I'm not going to prove it. The reason is actually I can prove. Actually, I can prove it. This is just a one-step proof. Want to show you this is proof, but you don't have to. Is this? But it's a constant, so it's 1/4 or okay. And because the independent variance are sum of the variance. Okay. And this variance sigma square. So it just so you can easily generate when this n and n square, n. Okay, but I mean the general proof in the slide, but it's not necessary. But just trying to show you that is this. But what does that mean? Okay, let's look at the graph. You will see what happened. Okay, in the previous example, if you have sample size of 1, right? Remember what you have is 1, 2, 3. The probability of that is the probability is 1/3, 1/3, 1/3, right? If you do sample size of 2, we're here, right? Instead of 1, 2, 3, you will have 1, 1.5, 2, 1.53. Right? The probability will be 3/9, 2/9, 2/9, 1/9, 1/9. Okay. Actually, you can see that basically the number are closer to 2, right? Because this do the same. Okay, and this is separated into these 2 parts. Same here. Okay, and this number basically coming from extreme number, right? How you get sample mean of 1? You withdraw this number, always get 1, or always get 3 for this extreme number. Okay, and actually, if you go one more step, right? The probability extreme number are getting smaller. More likely that you get more data in the center. Okay, and that means the variance gets smaller, right? If you think about this in graphical form, it's like this, right? Suppose this is I know this is the x, okay, and you talk about this when you have sample size of 2. Okay, sample size of 1 actually the same, right? This is sample size of 1, and when you try to get it smaller and smaller, this sample size of 3, so on and so forth. Actually, the variance drop. I should be more careful because it should be If you this probability, that should be higher because the area should be 1. Okay, so the variance gets smaller. Basically, you just say it, the sample mean squeezed to the center. Okay, so okay, so that is the formula. I prove it for you, but you don't have to know the proof. But the idea is like that. Okay, when what here is one important thing actually we don't talk about right now, but there's a one important property. When n, you can see this one, when n go to infinity, n get very big, the variance basically nothing. It's 0, right? That means that when you have many samples, we call it many infinite many times, then there's no variance. You get exactly what you want. Okay, that is what we call, we don't prove it here. What this is called law of large number. Okay, that's what it means. This goes to mu. Okay, I don't want to talk about conversion probability, but what it means is when n gets very big, right? Or okay, I'm not doing it very rigorously, but that is what it means. There's no uncertainty there when n go to infinity, right? Because variance go to 0. Okay, and there's one notation here. Okay, it's important notation. It's called, this is what we call standard error of the mean. This notation actually means standard deviation of sample mean. Okay, just the SD. Any question? Okay, but I think it'd be good we give example before break. So the example convince you that this formula is right. Okay, of course you don't need the example, you know it's right, but I have to convince you this is the right thing. Okay, again, we have the 3 number 1, 2, 3. Sample means 2. How to calculate variance is to take each observation minus the mean, right? And divided by how many of them. Okay, do note that's population variance. Cool. That's why I divide by 3 because n is 3. So the sample, the population variance is 2/3. Okay, if you have sample variance is 1 because 2/2, but here is 2/3. Okay, and now what are we going to prove is to try to show you that this is the right formula. Okay, because sigma square is 2/3. Okay, so we want to show that the variance of the sample mean is actually 1/3. Okay, 1/3, then it's actually what we want. Okay, 2 is 1/3. Okay, so this is a proof. Again, this is a graph here. Okay, every entry have probability of 1/9. Okay, and we know the sample mean is 2. Okay, we want to calculate the variance of this. Okay, to know that we're talking variance of the random variable. Okay, so basically you just take each observation minus 2 and take square times probability, right? Just remember the variance formula. Variance of x is summation x minus x squared times probability x. Okay, so each observation is realization is 1 minus 2 square is 1, and you have 2 of this, 1 and 3 satisfy this one. Okay, and you have 1 minus 5 times minus 2 is 0.5. Okay, each 4 of them actually is 0.5 away from mean, and all these are gone because 2 minus 2 is 0. So that's why you have 2 plus this is 1/4, right? So 1 plus 2, 3, 3/3 is 1/3, which is what we said here. Okay, so let's have a break. And we'll resume in 10:30. I guess we will continue. So this here the proof of what I said here, right? But I'm not going to go through. So here comes the most important theorem beside what we have the law of large number. Here is what we call the central limit theorem. Okay. So the central limit theorem. So the central limit theorem basically said the following. Okay. If you have large enough sample, okay, we know that the sample mean is exact when it's this guy actually exactly same as sample mean, right? And but we can actually show, okay, this particular guy is standard normal. Okay. So what it means, the sample mean, okay, would follow a normal distribution. Okay, we have actually know from the previous, before the break, we know sample mean have the same mean as the population, have variance as n fraction 1/n of this population. Okay, this is where it's shown just before the break. So what is the crucial in this thing is, regardless of what underlying the x looks like, may not be a bell curve, anything. Okay, and turn out to be the sample mean is normal distribution. Okay, we'll exploit this fact for the rest of the whole class. Okay, because the good thing is we don't need to know what the underlying thing looks like. Okay, if we have large enough sample, okay, under random sample, and we have the sample mean as a normal distribution. Why this is crucial? This is not necessary for the next class, estimation. Okay, we need to know, we don't need to ask what's underlying distribution. We don't have to understand that. As long as we collect enough sample, okay, and satisfy certain condition, that we can assume this guy follow normal. Okay, when this follow normal, we can do a lot of stuff, right? Because we can put some estimation, right? Because if we don't know it's normal, how can we estimate, right? We don't know how what the x bar looks like, then we cannot talk about estimation, right? So turn out to be the good thing is this sample mean turn out to be a bell curve. Okay, and then we can say inaccurate how to guess what should be the what should be the sample mean where they are. We can have some probability statement on what are we estimating, which we will cover next class. But that is very crucial thing we have to do. Okay, without this, there's nothing we can do for the rest of class. It's a very important statement. Let me repeat again the statement because it's so important. It's worth repeating. Okay. So again, let me repeat again what is this statement is about. Is we know the sample mean from before the break have same mean as population one. We know its variance follow the sigma square over n. We know it already. Okay. So the crucial of this central limit theorem is this sample mean is normal. Okay, it's normal regardless what underlying looks like. Okay. Remember the question about the living space. We don't know what's going on. What's the distribution, right? About the mirror case, right? It's a binomial. I mean, the thing we talk about proportion, but central limit also apply in that case. Okay, we'll talk about this immediately about proportion, but it doesn't have any restriction. Okay, anything goes. Okay, anything whatever looks like go to normal. And of course, when this normal, this is standard normal. This is what we learned last class. Okay, so if you go to advanced classes, this is the exact statement. Okay, of course with some limit. Okay, and this basically imply this. Okay, so this is the formal statement. Of course, you have to put some limit here and there, but so that's why we talk about this. Okay, not talk about it, but this is the thing we want. Okay, So the question probably you want to ask is, this thing works for very large sample, right? Or has a claim. So how large in practice you need to go? The rule of thumb is at least 30 something. Okay, if you less than 30 something, then you do not have normal. Okay, if it doesn't look like a bell shape, it looks like something else. Okay, what it looks like, it depends on what the underlying population is, which we don't know, have no idea. Okay, so that's why when you see sample, okay, you will see at least you need this number. Okay, if less than this number, we don't know too much. So that's why you probably pick up whatever science journal. Okay, and you will see most of the time at least you can do 30 something, right? I mean, less than 30 something is probably not a good way to do things, but this is how this is important. Okay, so now I hope this can convince you, but let me give an example of this one. But of course, this example is not much application right now, but we will save it for the next class. Okay, but this is crucial. Here is our population with mean mu and variance 64. Okay, I didn't tell you what is the distribution of this. Okay, it can be binomial, it can be exponential, or whatever. Okay, it didn't have. I don't know what it is. Okay, but I do a random sample with size 100. Okay, I don't know what it is. Okay, and just I know I want to draw 100 sample from there. Okay, the question is, even though I don't know it, I want to ask, I take the sample mean from this sample. Okay, what's probability that is no more than 4? Okay, it looks like a hopeless question because I don't know what it is. Right, I just draw some sample, I calculate sample mean. Okay, what will it looks like? What probability? Can you say anything about what probability? The good thing is, by central limit theorem, we know this sample mean actually follow a normal distribution. Okay, so this is the power of central limit theorem. Is we don't need to know what underlying is. Okay, that's very important for application because we don't know what is the distribution of say income in the world, right? In the whole society, we don't know. Okay, what is the living space in Hong Kong? People are average living space for Hong Kong people. We don't know. Okay, no one knows what it looks like. Is it going to left skew, right skew? It's going to be a lot of kurtosis, a lot of big variance, small variance. We don't know. Know nothing about those. Okay, but the fact is, I don't care. Okay, what I tell you is, as long as we know some of the, as long as the variance, okay. Or of course, you may ask, what happened? We don't know the variance. They will be recovered at the end of this class. Suppose you know variance, okay, and that's done because this thing is normal. Okay, and this is following the normal with mean 5. Right, variance will be 8 over root of 100. Right, because just to remember the standard error, okay, will be this, right? And sigma squared is 64, so sigma is 8. Okay, so this is 10, 8 over 10, right? 0.8, right? So it's negative 1 over 0.8 is 0.1, negative 0.125. Okay, so how to calculate this? Probably you still remember. This is just norm as this negative 1.25 true. Try to convince you. Hopefully they have Excel, or I don't know. Yeah, they have. So just to convince you this is the right number. Again, we have norm as this 1.25 and true. Oh, sorry. True. Okay. 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 So this is this number, same as that number. Okay, so that's how I figured it out. Now, is that okay? I mean, in case of it, I mean, just to make sure that you see it. Is that okay? So how to calculate from here? Okay, just to remind the significance of this central limit theorem is we don't need to know the underlying distribution of the population. Okay, we only need to know the variance and the sample mean, then we're done. Population mean, then we're done. Okay, of course, you may ask how we know all this. Okay, and we'll talk about this next class. Okay, and we actually don't need any of those. Okay, we just collect a sample, we can do a lot of things. Okay, this here we just assume we know what we can say about it. But next class we'll talk about we don't need to know those populations. We don't need to know 5 and 64. Okay, and we don't need to know 64 after at the end of this class. Okay, just wait a little bit. We don't need to know 64. Okay, and we don't need to know the 5 the next class. Okay, so these all the 5 and 64 are we don't need this information. Okay, but just for the sake of this discussion, we talk about we know them here. Okay, is that okay? So this is the significance of this, but we'll talk about a little bit more. So there's a graph, right? This is the C here. This area is 0.1. Okay. Now, the next part is talk about a particular case of sample. Okay. So far, the X have no restriction. X can be anything, right? Because we don't care about what is underlying X. Okay. Consider the special case where each observation is 0 and 1. So what's that? Right? Just remember the scenario. Okay. And just remember this case. As a leading example, we have at the beginning, right? We have the question like this. This is CHK. Okay? And we ask people whether they like mirror, not a big fan, so on and so forth, right? These are for people, right? Then suppose we have this data, how many people who like mirror or not mirror, okay? And if we know this information, there's no uncertainty, right? That means that there will be pi of them, pi proportion, right? Maybe the big one. Remember, original cases we have 1,000 students, right? In the B school, okay, and we know 600 of them like mirror and 400 doesn't, okay, and we will call this pi is 0.6. Okay, it's proportion. We call this population proportion. Okay, when we talk about just like or don't like binary data, this is maybe this is called 1 and this is called 0, right? Here is a good example of what we learned, the random variable, right? The outcome is either like or doesn't. We just assign 1 or 0 to here. Okay, and here we have the proportion. We call sample proportion is this, right? So in other case, the observation here is X is either 0 or 1, right? X is either 0 or 1, right? And this what we call the sample mean, right? X bar is sum of this, okay? And this particular case, we call this sample proportion because it's either 0 or 1. Over n, this number is also between 0 or 1, right? Because at most everyone is 1 over n is also 1, right? It's the sample mean is what we call the sample proportion, okay? And now, the interesting case of this is because here is the B school student who like mirror or not, okay? The question is, suppose I draw one particular guy there, okay? What's the probability he like mirror, right? It's 0.6, right? This is the binomial trial, okay? And now if we draw n guy, randomly. Okay, how many people who like this? That is a binomial. Okay, but you just ask one guy. Okay, then each observation, okay, is a binomial with probability success pi, because whether light is 1, right? So we learned that from the previous topic, the mean is same as the pi and the variance p times 1 minus p. If you still remember that. Okay, if you don't, let me go back to the slide to remind you this is the case, because I think it's the reason why we studied that, right? Go back to the slide. Where is that thing? It's here. Just wait a bit. Here. Getting too big. Okay. Here, Bernoulli, fair success. We learn this is P, this is 1 minus P. Okay. Each observation is following the Bernoulli. Okay. Exactly here. Okay. Do remember why this is the case, right? Because if pi is close to 1, then basically everyone likes mirror, then you don't have surprise, because the sample you collect is also 1, right? If everyone don't like mirror, then same thing. Okay. So this is the thing, okay? And this is nothing new, right? But just saying that if your data is only 0 and 1, this is called sample proportion. Okay? And each observation, actually, you know, in this particular case, is Bernoulli. Each one you collect. Okay? So that's much easier, because you know the underlying thing is like this. Okay? And the good thing about this is, first, this is special case of the standard case. So sample proportion, which is sample mean, so same as the population proportion, which is population mean. Is that okay? Because this is the population mean, right? Add up everything divided by n. Okay, just to repeat, this is exactly the same thing. We said sample mean is expectation, is population mean. So here what it said is the sample proportion, the expectation of the sample proportion is population proportion. Okay, just to repeat, the idea is what we do is, if you try to talk to some B school student, you collect all this once, twice, 3 times, you collect many of them. Okay, average of those proportion will get you 0.6, which is the actual one. Okay, is that okay? Is that okay? Is that okay? Good, good. Oh, good. So now, what's the, why we focus on this special case here? Is the mean and the variance are related. Okay, just to go back to the previous slide here. You know that the mean is this guy, the variance is this guy. Okay, so there's only one parameter here. There's no mean and variance are related. If you know the mean, you know the variance. Okay, so that means that the variance is pi times 1 power n, right? Because each one is variance pi times 1 minus pi. Okay, so that means the standard error proportion would be this guy. Okay, so now the interesting part is the following. Okay, is the central limit theorem applies. Okay, in particular, okay, everything the same. This is the mean. This is the standard error, right? This is just x bar minus mu over sigma over root n, because this is sigma over root n is the standard error. Okay, so this sample proportion minus population proportion over standard error. Okay, just to just make sure that you understand this is, let's go back to here. Sample mean, population mean, standard error. Okay, so there's nothing new here. Just plug in the special case. Okay, nothing new here. Okay, so the sample proportion. Okay, I don't need to know this guy. Okay, we know all this. Okay, suppose we know the pi, then we're done, right? So that's a very good thing, right? And of course, we'll talk about how to apply this, how to use this in the next class when do estimation. But this is very important. And you may ask when we can use this, okay? And of course, this rule of thumb is not really important because we never know pi. But anyway, for this one to hold, you need n pi and n times 1 pi at least 5. Okay, so so that can be an issue because pi can be very small, or 1 minus can be very small, right? Because say, for example, is how many people in the population say have the COVID, right? In Hong Kong, the pi is very small, right? So you want to estimate how many people get COVID in Hong Kong, that will be very complicated, right? Because say for Hong Kong in this case, maybe you had 1 or 2 people, right? So it's 1/6 million, right? In that case, you have n is very big in order to make it to at least 5, right? So that means you have a little bit hard time when you talk about extreme event. But talk about mirror is should be okay because looks like it's easy to get, right? Suppose for this particular case, right? When we should apply for this, right? The pi is 0.6, okay? So 1 minus pi is 0.4, okay? So how many samples we need to get this good rule of thumb? So n times 1 minus pi to be 35, is 5, okay? So n times 0.4 is 5. So n is 5 over 10 over 4. So you only need 30, right? So 30 is fine because 12.5. Is it not clear? Maybe around there. So here is we have 0.6, okay? So we want n pi times n 1 minus pi is at least 5, right? So it's either n times 0.6 bigger than 5 or n times 0.4 is greater than 5. Okay? And this is 5 times 6 over 10, 5 times 4, 10 over 4, right? So this is 2, this is 5, right? 12.5. Okay, so in that case, you need to be bigger than the smallest. So if you have 13, then it should be fine. Then this would apply. Okay, and if you're less than that, okay, then you have to consider binomial again. Okay, so actually what is said is this thing is binomial, right? So the sum is binomial, just binomial over n is also binomial. Okay, so this is a the sample proportion looks like binomial, okay, just divided by n. And but what is said is when this n pi and n minus pi is bigger than 5, you don't have to consider binomial, you just consider normal. Okay, so that is actually behind the idea of binomial can be approximate binomial. As I said, right, the bell curve is useful to approximate binomial, but we are not going to talk about that because we skip that part. Approximation here. Okay, just mentioned, right? If this follow binomial with this, okay, And this guy basically a normal. Okay, but we're talking that because this is no longer useful now. This is only useful in the old days when you don't have good computer, and binomial you have to calculate many factorial, right? But this one is a good thing in the old days. But just now you know that is something because that comes from center limit theorem. But anyway, we're not going to do anything about that. Skip. Okay. So I guess what I want is talking about the last thing. Okay. This is unknown variance. Okay. What are we talking about here is, remember this example here. Okay. I mentioned that we need to know the mean and we know this population variance and the mean both in order to do the calculation. Okay. So I said we can do away with 64. Okay, we just take away 64. This is what we're going to do. Okay, but of course, we take 64, you're no longer normal. You will be what we call student T. Okay, but that would be the goal. Is take away 64. Okay, so that's the goal. So why we want to do this is because, okay, central theorem tells this one. Okay, but that is not very useful. The reason is sigma, we never know. Okay, the population variance we know. Okay, the sample mean can be we know somehow. Okay, it's not. Sometimes we may have some idea of the sample mean. It's not something terrible to know. Okay, sample variance is very hard to know. Okay, how can we know sample mean with some idea of sample mean? Because what is the average living space in Hong Kong? Probably we know, right? Because look at how people live and you have some idea. But to guess the mean is easy. To guess the variance is very difficult. Okay. But regardless of what we will talk about, we don't need the sample, the population mean. But anyway, suppose the first thing we do is the simplest thing first. We don't know sigma. Okay, what can we do? Okay, so assume we still know mu. Okay, but we want to do away with sigma. Okay, so as you learn in the topic 1, okay, you know the population variance and sample variance. Okay, so what actually we're doing here is we don't know sigma. Okay, but we used our sample to calculate the sample variance, which is S, which is this guy. So data minus the sample X bar sample mean. You know that these two are random variable. Okay, this depends on sample you draw. Okay, this guy, okay, S square. Okay. The question is, if you use S square, okay, we don't have sigma. Okay, we place this here. The question is, what would this guy looks like? Okay, because we don't know sigma, right? Suppose we place this guy. So what this guy looks like? Okay, turn out that this guy is a distribution of this one, student T. Okay, and of course we talk about some idea behind the proof, but we're not proving it, but just some idea. Okay, so what is this? Okay, what is said is I know the sample population mean. Okay, that's the only thing I need to know. Population mean. Okay, okay, I make some guess. Okay, whatever. Okay, I know population mean. Okay, and I can calculate this guy from data. Calculate this guy from data. Calculate this guy from data. Right, and then I know how the sample mean looks like. Okay, so that's would be the thing. Okay, so we may ask why this student T. Okay, we'll talk about that after we give example. What is this first? But if you still remember from the maybe I give you the idea first because that would be not difficult to see. Maybe I give example first because that would be okay. So example first, then I explain why this is true. Okay. So remember this actually the exactly same question. Okay. But now we don't have the population variance. Okay. We just know sample mean is 5. Okay. And now we're sample 100, same. But now we are from the sample, we know sample mean is sample variance A. Okay, that is coming from the calculation. Okay, you collect a sample, 100 sample, calculate sample width. It's like now the question is asking what is the probability that sample mean is no more than 4.5. Okay, and here actually that is coming from the theorem we have, x bar, which is a random variable minus population mean over the standard error, right? 8 over 100 is T99. Okay, why 99? N minus 1. Go back to the statement. The sample mean minus the population mean over the sample standard deviation over the this is standard error, right? So this is what we call, okay? And here you can see basically it's this guy, okay? You minus the 5 over this gives you T99, okay? And how to calculate this, okay? This guy is negative 1.76, okay? And this is just the Excel statement, T this negative 1.796, 99, true. Okay, I will show you in the Excel. Okay, but before we show it, you can see if you use the Z, it's very similar. Okay, so the thing is actually, you look at you can play around with Excel. When N is more than 100, okay, whether it's T or Z, will not make a big difference, will be very similar. Okay, but when you have sample size less than 100, you have to be very careful, they can be very different. Okay, so you may say, oh, if I do big sample, okay, doesn't really matter. Okay, you don't have to learn this. Okay, you can basically use the sample variance as a population value, doesn't really matter, this is normal. But when the sample size is less than 100, usually you don't have more, usually you don't talk more than 100, usually 60 or 80. Okay, then you have to be very careful, you have to use T. Okay, so let me show you this Excel first. We have T this negative 1.76, 99, true. Okay, 1.768, I guess. Okay. Okay, 1.768. 1.768. Yeah. Why cannot? Okay. So this is how this number is being get. Okay. Now I want to give you the reason why this is student T. Just very brief. Here. Okay. And as I claim, so the simplest thing, I'm not going to do any proof. Okay, just give the idea. So the key step of this is we don't prove, but we learn chi-square. So this part is actually chi-square. Okay, and we learn this normal. Okay, so what it is this is a normal over a chi-square, which is called student T. Okay, we're not going to do any proof because that is too complicated. But just to remind you why this is the case is because what is T? If you remember this equation, okay, T is the standard normal over a chi-square distribution. And the thing that we have here you can imagine that we have a divided by sigma over root n. Okay, I have sigma here. This is a normal, and S over sigma, okay, which is this guy. Is a chi-square over n minus 1. Okay, so there's a reason why this student T. Okay, and the reason why S is n minus 1 because we can prove this is turned out to be the sample variance over the population variance. Okay, is actually a chi-square distribution. Okay, but we are not going to do any proof on this. Okay, and but that's the main goal of this one. Okay, so just to recap what we learned today, I hope that would be something that is important. Okay, so what we learned is with some sample collect. Okay, either the sample is a number or proportion. Okay, and under simple random sample, so we have certain property here. Okay, which is simple random sample. Everyone have the same mu as the underlying population. The variance are the same. Okay, and zero covariance. And here the sample mean is adding up or divided by n. Okay, and the property will be the mean of sample mean is population mean. Okay, the variance of the sample mean is 1 over n of the population one. Okay, the standard error is just take the square root. Okay, and we have central limit theorem set is we can further set if n is go to infinity, where n is very large, we have a normal distribution. And here is same when we have a proportion data with 0 or 1, the same idea. But the only difference is this guy, okay, they're related by this. Okay. And again, central limit theorem apply, same thing. Okay. But here we have much better. We need not need to know this. Okay, it's much easier because we know the sample mean, we know the sample standard error. Okay, so it will be very useful for the next class. And lastly, we have what we call the unknown variance, which said if we have no idea of the sigma, okay, which we never know, okay, and then what would be sample mean looks like, okay, and suppose we know the mu, okay, which will be very useful later, okay, but this guy, okay, will follow a p distribution. Okay, so you may ask, just give you some clue, okay, why we care about all this, okay, why I care about this, okay, and one of these, look at this particular example, would be what we call hypothesis testing. Okay. For example, the question is like the following. Okay. Suppose look at a packet of food. Okay. And the packet of food may be, I don't know what it is, maybe milk. Okay. And the milk claim have 5 grams of, say, protein or 5 grams of probiotics. Okay. And if you want to, as a quality control or as a government, right, you want to see whether the claim is right. Okay. And then what you're going to do is collect sample. Okay. You collect 100 box of milk, right, and see if this is what they claim is right. Right. So what we're going to do is you collect data, you calculate sample variance, you can do, right, and you calculate actually you get 4.5. Okay. Then you try to see, okay, is what the guy said is true. Okay, let me repeat the statement. Okay, is someone claim the thing is 5. Okay, you collect a lot of data there. Okay, calculate the sample, you get the number is 4.5. Okay, you want to evaluate whether that guy is telling true or not using the data. Okay, look at the data. Okay, calculate probability of this happening. is very low. Okay, so what it is the following. This what is the hypothesis testing is about, which we will talk about this next week with the following. Right? You assume that guy is true. Okay, that means that the X bar, according to the central limit theorem, the Bell shape. Okay, if that guy is true, this sample mean, we have the sample, this mu. Okay? You claim this out. Okay, but what you get, the data tells you is here, 4.5. Okay, so it's far below that. Okay, you want to say this guy is cheating. Okay, but the guy said no, you do sampling, happen to be down, is very low, right? It can be anywhere, right? You do sample. Okay, how can you say this guy is not an honest guy? Okay, look at this here. The probability of this is super low. It's 4%. Okay, so in statistics, what we're trying to do is, if you're far away from what they claim, okay, how to determine far away? This probability. Okay, if the probability is very low, say this guy is cheating. So that is what we'll do 2 weeks next week. Okay, and that is what the goal is. Okay, and next week we'll talk about the following. Okay, is suppose we don't know this 5. Okay, forget about the 5. Okay, what we're going to do is, if we collect, I don't have milk, right? I collect 100 milk. Okay, I can calculate sample mean, which is 4.5, right? In this case, and I have the sample variance. Okay, then I can estimate what is the population mean, which is average milk content. Okay, so that will be doing next week. We'll be asking, or actually Wednesday, to estimate, right? We don't know 5 here. Okay, we want to estimate the 5. Okay, or look at the mirror problem. Okay, although here I claim 600, 400. Okay, so there's no way we can know for sure, because if we know, we don't have statistics, right? We want to guess how many students in CUHKB school like mirror. Okay, what we're going to do, you're going to pick up some sample. Okay, and you say, oh, 10 people say, okay, 5 of them like mirror, some of them don't know. Okay, what we will guess? The guess will be half of people like mirror, half of them don't. Right, that's what the best thing you do. Right, but you don't stop there. Okay, you don't stop there. Right, suppose you have this. Right, you have 10 guys, 5 guys like, 5 guys don't. Okay, and then you get, okay, 50% of people in CHK like or don't. Right, but you don't stop there, because this will be too easy. Right, so you're going to go one more step. Okay, can we have better guess? Much better. So can you give a interval such that we think it's very likely to be inside? Okay, maybe can we say something like, this is 0.5, right? The probability, the proportion, right? Can we say more accurate? It's very likely to be, say, 0.48 between 0.52. Okay, this we call interval estimate. Okay, if we can, that is how likely we've been inside, right? So what it means is, the probability that is within this is large enough. So we need to know. That's why we need to have understanding how they distribute. Okay, we can make a guess, right? What it should be. Okay, so that's what we'll talk about in the Wednesday. So as I said, next class, I don't think we can finish all the lab assignment. So lab exercise. So we will be making, I book the lab again. So basically, likely Monday we will do in the lab, not here. So next Monday we will do it here. Okay, not here. So in the lab. Okay. So I guess I should stop. Just remind you the homework. This Sunday. Okay. So I see you see you on Wednesday in the lab.